So I'm Jesper. I used to be part of the GAIA, both the organizing committee of the conference, but also part of the board as well at some point. So I have some history with GAIA at least, and there seems to be a lot of new faces, at least partially in terms of attendees and so on. And there are a few local Ericsson people and so on. But anyway, so what I will be talking about is machine learning at Ericsson, you could say, but at the same time, I'm part of one part of Ericsson that's called Packet Core. So you should keep that in mind that it's a relatively small part of Ericsson in general. But so I'm part of this machine learning group at Packet Core. But first, the mandatory information about Ericsson that you have to show in some way, but I'll do it really briefly. So Ericsson globally is around 100,000 employees. I think we're like 10,000 in Sweden, if I remember correctly, something like that. Majority being in R&D in Sweden. And for comparison, I think Google is was 60,000. So we're, at least in terms of headcount, we're larger than Google. Here in Gothenburg, we're in this particular building, we're around 2,000 people as well. I think all over all departments in this building, I think we are on the order of 100, maybe 200 data scientists locally here. Globally across Ericsson, I have no idea, but more. I think it's a safe bet anyway. Right, so the purpose of this talk then is really to talk about kind of how your modeling decisions, or whatever model you pick and choose, how that will impact your actual deployment, or kind of whatever deployment you will get based on that model. And the realization that your modeling selection has a huge impact in terms of how you deploy your model, how you lifecycle manage it, and so on. So the purpose of this talk is to have a relatively high-level description of a particular use case that we happen to have. And then I've shown a few examples of models that you could deploy for this use case. And then the idea is to kind of discuss around what kind of downstream result would you get if you pick one model over the other in some sense. So first, let's start with the basic use case. So in any cell phone network, or that's true even for Wi-Fi in some sense, one big thing about it is mobility. So the point where you need to kind of move around in the network without interrupting the traffic. That's kind of one of the big differentiators, I would say, between, let's say, a telecom network and, let's say, Wi-Fi. Nowadays, you can kind of do handovers in Wi-Fi as well, but it's not nearly at the same level as you can do for a cell phone network. So the short version of this is that on an extremely high level, you have essentially for 4G at least, a cell phone can act in two different modes. So it's either in active mode or it's in what's called idle mode. And so for active mode, as you're moving between base stations, these kind of antenna things are supposed to represent base stations inside a real network. And as you're moving inside that network, and you're also simultaneously sending payload, sending traffic. You're browsing YouTube or doing whatever. If you're actively doing something, that means that your radio and everything is actively talking to the network. So then you need to kind of, as you're moving, you need to, in a controlled manner, kind of move over information between these two base stations or access points if you want to kind of stay with the Wi-Fi nomenclature. So normally in active mode, when you're moving between two base stations, you send what's called a handover request. So basically saying that I'm at eNode B1 here, I want to go over to eNode B2. So then the cell phone, the car in this case, will send a handover request saying that I want to go to eNode B2, and then you have some communication going back and forth saying whether that's okay or not. And this is a very extremely high level kind of description of how a cell phone network works, but on an extremely high level. So essentially you have base stations on the left-hand side, and then on the right-hand side you have something called an MME, which is a mobility management entity. So essentially the role of the MME is to kind of make sure that these handover requests and the mobility in the network works. And then as you're progressing further and further backwards in the network, you get kind of different roles in some sense. But what we're interested here is the MME, and the use case that we will be talking about is mobility and mobility prediction in principle. So the kind of the complicated part is when a user is actually in idle mode. So idle mode is when the cell phone, and sometimes I use the word UE here. UE stands for user equipment, so that's essentially your cell phone. So when your cell phone hasn't submitted anything for some period, so you haven't actually browsed YouTube or done anything, then your radio will go down into something called idle mode. So that means it won't talk to the network anymore in any sense. And that's basically just to save battery in your cell phone. So the quicker you can kind of disable the radio, the more battery you will have in the cell phone. But the problem is you should still be able to receive, let's say, an incoming call. Somebody is calling you, or you get a push notification or whatever it may be. The cell phone still needs to wake up and kind of enable more of its radio resources to kind of be able to deal with that incoming traffic. And the problem is, if you've been idle and you've shut down the radio in some sense, then the network doesn't really know where you are. Because while you've been idle, while you've shut off your radio, you could have moved anywhere inside the network, and you don't really know, the network doesn't really know where you are. So if you have, I'm not supposed to walk around, but I'll try to stay fixed. So if you get something incoming in this direction, let's say an incoming call, and the car in this case has moved around, there's no way for the network to kind of know exactly which base station is closest to that car. So on a very high level, essentially what it does is it needs to send this paging request to a group of these base stations, saying, essentially just asking, is this where you are, or is this where you are? So it's kind of almost broadcasting to a bunch of different base stations, kind of asking the car in this case to kind of wake up and enable more of its radio resources so that it can start receiving actual data. But so this is essentially the problem. So how can we find the car with as few signals as possible? Because you can imagine if you have, let's say, a really, really large network where let's say you have 30,000 of these base stations, you don't want to send 30,000 signals individually to each base station. So the problem that we're trying to solve here, how can we be more intelligent or more clever in terms of figuring out where is the actual user at this particular time? So that's the base problem. So on top of that, I mean, if you would write an academic paper, that would probably be enough. You get some data set with whatever features you have in that data set. You think that, oh, well, it's about finding a base station in this case. So a simple accuracy metric is probably good enough. And then you write your paper and you publish it, and then you're happy. But then reality strikes. Does accuracy actually matter? Is that important in this particular case or not? And the reason for I'm bringing this up is that usually when you develop some feature in this context is that there is so much more things that has an impact on your model decision than strictly accuracy. And so kind of the continuation of this talk will be around like what other factors there could be that impacts it. So the product context in this case just explaining again a little bit about like the product itself. So now we're talking again about the MME particularly. When this now it gets complicated, I realized, because when I did these slides, this was a few years ago, and at that time it was what you would call an embedded product. So it's essentially a box that you sell to some customers and they set it up. Nowadays it's like slightly more, let's say, cloudified in some sense, but that's not strictly true either, because we still sell them as a box, even though they happen to execute inside a cloud. So from a conceptual point of view, you could view it as an embedded product in the sense that we're selling it, and Ericsson as a provider, after that point, we're essentially hands off. You can't really touch the product. Usually they don't even have an internet connection at all. Well, of course they have an internet connection, but you don't have access to the management interface inside the MME. So you can't really do anything from the internet side. So we as a provider can't really get access to it after the customer has installed it in their network. So whatever we do inside that box, it needs to work, hopefully at the first try, and it should never break, essentially. And if you've done machine learning in production, you know that never happens. It always breaks. So it's a really, really challenging task in that sense that when you're doing business to business, it gets slightly more complicated because you're no longer kind of operating the system that you've actually sold in that sense. Not really important in this particular case, but we could also mention that one MME in this case is roughly equivalent to 10 1U blade servers, if you're interested in that types of stuff, and each MME handles around 1 million users. So you can imagine something on the level of Sweden, you would have something on the order of 10 to 20 MMEs handling all of Sweden for one operator. So every operator has their own system of this. In this particular case, it also means that the MME is implemented in Erlang. So it's not, or traditionally it was not a, let's say a Kubernetes pod where you could arbitrarily start containers and do things kind of side-loaded things in that sense. So everything had to run inside Erlang. That was kind of the one thing. That's not strictly true anymore, but when this was done, that was true. And also really, really important to keep in mind is that for pretty much every box in the entire network, so all the way from the base stations to the MMEs and all that stuff, capacity is really, really important, super important. So every CPU cycle, memory or whatever that you use for machine learning, that means that you're using cycles that won't be used for actually running the network itself. So everything has to be super efficient, or at least as efficient as possible. And also, obviously, no GPUs. You don't even have basic arithmetic in Erlang in that sense, where you can actually use SIMD instructions or GPUs or anything like that. That doesn't mean that you can't do it in Erlang, but you have to do C bindings. So from Erlang you call into some C library where you do the actual work. That doesn't mean that you can't do it like that, but it makes it slightly more complicated. Yeah, and just to kind of ground it a bit in terms of physically what we're actually talking about. So this is a map of Lindholmen area. So this is actually where we are right now. I would say we are, I think that's where Ericsson is, the current building. I think so. But here you have Lundbyleden, for instance, going through, and this is a real map of a real InnoBs in this particular area. I don't remember exactly which operator I took this from, but this is open data, so you can get GPS positions for all base stations pretty much all over the world, if you want to have a look at it. But the purpose of this slide is just to show how many of these base stations we're actually talking about in terms of physicality. So if we look at Lundbyleden here, typically you have, on a relatively short area, you have 4 possible base stations that you could be talking to. So if you're traveling along Lundbyleden, you're not guaranteed to strictly speak to one InnoB or some other InnoB. It depends on like the current load of one particular InnoB. So if one is overloaded, you may start talking to another one and so on. So you could argue from the MME's perspective that there is some noise component in terms of the InnoB selection here, which you can't really model from the MME's perspective. Of course, if you had full access to all the data, you could probably model it, but that's not how it's designed today. So let's say, as an example, if you had, let's say, radio measurements where you know exactly what is the signaling strength from all these 4 different InnoBs, for instance, maybe you could make some guesses, but that information is not available inside as part of the MME, so you can't really use it. And the reason for why I bring that up is about, I would say, out of all of the academic papers I read specifically related to paging, this exact problem, it's quite a popular problem academically, if you talk about telecom at least. I'd say about half of them kind of cheat by using kind of synthetic radio data and all that stuff that's not really available in a real network in that sense. I mean, it would work if you would build a completely separate paging thing that's outside of the MME and sits somewhere in between the base stations and the MME in this case, but no real network actually is built like that. Yeah, so very quickly before we fall asleep, I know not everybody gets as excited about telecom networks as maybe me. But so before we started doing this work, there was one function inside MME that was there already called smart paging. So in this case, I'll call it legacy. And the way the legacy smart paging works is that essentially it always, when it tries to identify these cell phones, it kind of does it in an iterative way. So it doesn't start by paging all these 30,000 InnoBs, for instance. It does it in an iterative way. So it starts by always paging the last InnoB where this UE or this cell phone were last observed. So if it went idle in InnoB 2, for instance, as in this case, the first thing it will do is try to page InnoB, because there is a high probability that the cell phone will still be where it was last observed. So that's usually a pretty good strategy. The second step is the way it used to work was this historical list. So we would just be kind of marking the last 10, as an example, the last 10 visited base stations. So like a historical trajectory of how the cell phone has moved through the network. And the assumption here was, when this was kind of invented, where at that time we didn't really have any data. And I mean, this was invented, I'd say, I don't know, 15 years ago or so, 20 years ago maybe. We didn't really have any real network data, so a lot of the functions were developed based on assumptions on how a user actually moves in the network and so on. So the assumption here was that, well, a user typically kind of moves in the same trajectories every day. I mean, you go to work, you go home, you stay at your home, etc. So the assumption here is that keeping this historical list was a good predictor in terms of where you tend to move around. Also, if there's any questions, please don't hesitate to interrupt me. And And I should say the kind of what we're talking about here is what in terms of machine learning is to replace this step 2. And then just shortly, step 3 and 4 is kind of just expanding that area where you're kind of paging. Tracking area is like a group of ENOBs, as we can see here, but not really important for this case. But the idea is that you start small and then you kind of increase the area in terms of where you're paging. Right, so again, examples here of, I mean, this would be, as an example, the last step here. So if we're paging the history of tracking areas, you would page both tracking area 1 and tracking area 2, which means you're sending messages to pretty much all ENOBs. So that's enough with boring telecom stuff. So let's talk a bit more machine learning then. So as I mentioned, there's quite a rich set of literature surrounding paging in general. Usually you can define those publications in kind of on a very high level, 2 types of models. So even what's called network level models or per user level models. So network level models are, like it says here, more about modeling the overall properties of the network itself. And there it could be that the individual user behavior doesn't really matter, but more if you happen to have been last observed in ENOB 1, then there is a high probability that any user that was last observed in ENOB 1 is likely to then go to ENOB 2, as an example. So that would be like a network level property where, I mean, if you're going through a highway, everybody's essentially going in the same direction, so there's no point in learning like individual behavior because all of them will be going through the highway anyway. And then we have user level models, which obviously then is like trying to model specific user behavior. So this user tends to go home, and these 3 ENOBs are the ones that are close to that user's home, etc. So there you're either learning individual users or some representation of a user and how they tend to behave. There's also kind of variations of that, of doing clustering and so on. Questions so far? No? So as part of this work, what we did when we started looking at this was that we developed about 1 billion different models to try to investigate this. And this is just a very small representation of all those different models, also including a lot of the models that already exist in the literature. And again, this was quite a few years ago, so I mean, an old school RNN, you almost never see that nowadays, but that's what one of the things we tried back then. But in principle, as an example then, so on the left-hand side, as an example, we have a very, very simple Markov chain. So essentially, if you were last observed in ENOB 0, you have some probability distribution of that user having gone to one of its neighbors. So just as an example, 70% of the users that were last observed in ENOB then went to ENOB 2. So a very simple Markov chain in terms of a probability distribution over all its neighbors. So this would be an example of a network level model. Another variation, another example is a simple RNN using LSTMs in this case, so this is an example of a per user level model. So here we're inputting the input is then a sequence of the previously visited ENOBs. So it's basically a trajectory. Another example of the input to that model is like the top visited ENOBs for that particular user, and then the time of day and so on. So you can put that all into an embedding space and try to predict something. But then on the output side, what's worth mentioning here is that, as an example here, we would have a softmax distribution over all possible ENOBs. So like the next ENOB where the user would happen to be at would then have a high probability if, like, node B4 has a high probability of being the next node B, as an example. But this softmax is an important thing to remember. So again, this talk is about what choices we've made on the modeling side, what impact will that have on the final solution? Yep.
Can the number of NOBs change after the third method?
Very good comment. Very good comment. We'll get there. But yes, the short answer is yes. Yeah, exactly. And they change quite rapidly. And I mean, especially initially when you start building a new network, like a new 4G network. I mean, you're adding new NOBs on like a daily basis. But then if you have a relatively fixed network, then it's less often. But still, that can for sure happen. And you also have situations where, let's say, an NOB breaks for some reason. So that NOB will no longer be part of the network until somebody actually physically goes out there and fixes it. So, and that could probably take a week or something like that. So then the question, do you want to have a suboptimal model for that week where it tries to predict that NOB that doesn't actually exist? Or, yeah, what can you do about it? Finally, also, I put up, just as an example, the dimensionality reduction. In this case, I think it's a TSNE projection of one of the data sets. So here it's actually kind of trying to cluster and group NOBs together that has a high probability of being neighbors, and then kind of projecting it into a 2D space. So this would represent a clustering approach in some sense. So, I mean, naively, you could think of variations where your output of the model is, let's say, a GPS position or something. So rather than predicting the next NOB, you're just predicting, okay, where roughly physically is the user in terms of the GPS position. You could do that. It's not very it's not very efficient, but there are some papers who have done that. Okay, so again, initially I asked if accuracy, is that a good measurement of this for this problem? So you can think of this is actually a multi-objective optimization problem. So for one thing, I mean, if you think again in terms of this procedure where you're kind of expanding the search in terms of where the user happens to be. So if you do it too iteratively, you're essentially paging one NOB at a time, then that means it will take a very long time before you actually find the UI, because you have to send a message, wait for a response, and then realizing that, well, it was not there, and then you have to page another one, wait and see what happens. So if you do that iteratively over 30,000 NOBs, it will take a very long time to actually find it. So while the kind of counter argument to that is if you page all of them at the same time, you will very quickly find the user instead. So you could optimize this problem for latency, but at the same time, you also don't want to send too many signals. So you don't want to send too many paging signals, because then both on the radio side, all those NOBs need to take care of all these signals. The MME needs to send all these signals. So it kind of explodes quite quickly if you want to page 30,000 NOBs for every single user all the time. So the argument here is that it's actually a multi-objective problem where you need to optimize for both latency and the number of signals that you need to send, number of paging signals in this case. But it's also a contextual optimization problem where in some cases you only care about latency, and in other cases you don't care that much about latency, so you can kind of sacrifice latency for reducing the number of signals and so on. So it would be good if this this kind of objective is tunable in one way or another, and that depends on the tunable in the sense of the from the user perspective. If it's an emergency call or an incoming call, you want to find it really, really quickly, as an example. While if it's broadband, it's not that important if it takes you a few seconds to get a push notification. So it depends on the user, but it also depends on the customer itself. Some customers really, really want low latency for various reasons, and others only care about number of signals because that means that they can have a smaller footprint. They don't need as many servers in some sense. Yeah, so here we have an example where we want to optimize for latency, just like I mentioned. So the simplest step here is just to page everything, and you will find the car, in this case, in the first attempt. And while if you want to optimize for signals, again, you could just page them individually, which will mean that you will have a fairly low number of signals, but it will take you a long time to actually find it. So given those two objectives, how can we actually evaluate the final solution? Since it's a multi-objective problem, and if we keep in mind the smart paging algorithm itself, let's say accuracy or F1 or whatever, is that actually a good measurement for this particular problem? What do you guys think? That's a very, very open-ended question. So, I mean, obviously there's a lot of different ways you can kind of evaluate this. So one thing you could think of is, for instance, Pareto optimality. Since it's a multi-objective problem, you can look at the Pareto front in terms of trying to optimize for both. You can also, of course, take the product between them and get somewhat of a univariate optimization. But then you have the problem of the scale between these two. I mean, what if a customer wants to optimize for one or the other, and so on. Another thing is, like I mentioned, you can choose from like a standards perspective, you can choose to page 1 eNode B at one step, or you can choose to page 10 eNode Bs at the same time. And there's nothing really from like a high level perspective that you need to do one or the other. So one way of looking at it is to look at it as a recommendation problem, actually. So instead of I mean, normally if you would, let's say, naively take accuracy, that kind of assumes that you're only trying to find one possible eNode B where the user happens to reside. But since we're actually allowed to page multiple of them, accuracy kind of gets a bit complicated in terms of how you should evaluate. So you could think of, for instance, looking at mean reciprocal rank, which is quite a popular measurement for recommendation systems. But again, so for mean reciprocal rank, essentially it just tells you on average how many eNode Bs in this case do I need to page to find it. Which also, I mean, sounds intuitive for a recommender system problem. But again, for paging, when the MME actually does the paging, it doesn't actually know how many eNode Bs it needs to page. So it needs to beforehand make a guess, oh, I need to page 10, or I need to page 20. And then even if the mean reciprocal rank on average is like 5, it's very hard to look at it on a per user perspective. How many do I actually need to measure? So I would argue that mean reciprocal rank, it does tell you something in terms of on average how many you need to page, but it doesn't tell you actually anything about like the final task in terms of what is the latency and how many signals did I actually need to send in the end in like the final real system. And here, yeah, so this is the final bullet here saying that spending a lot of effort on your evaluation metric would save you time in the end is doesn't have so much to do actually with machine learning per se, but I'd say, I mean, this is somewhat of a contested topic in the sense that some people argue that whatever evaluation metric you choose doesn't really matter because they're all correlated anyway. So even if you pick F1 score, the final model will be the same anyway. I don't agree with that. Yep.
The way you were introducing the topic, I also thought about recommender systems. What you told before the top 10 lab, and I was thinking if you think that GAIA classification problems with the imprecision array or ranking, and you get rid of probabilities, and you kind of differentiate based on how confident you are in the list of.
Very good comments. We'll get there, but you're absolutely correct. That's kind of where we're heading, in some sense. Yeah. So the reason for why I put the last bullet here is that my belief is that actually when you're starting to think about your evaluation metric, that is actually when you're starting to think about the domain problem. What is it that you're actually trying to solve in terms of your, like your kind of business objectives? In the end, what is it that you're actually trying to solve? And I would argue that it's the time you spend here is not so much about the evaluation metric, but it's rather understanding the domain. So for me personally, I think this is super, super important. Domain understanding is much more important than actual machine learning modeling skills in some sense. Yeah, and here we come to Josef's comment or question. Are eNodeBs or base stations, are they added or are they static? We've already answered it. So, for instance, if we assume that the network is not static, you have eNodeBs that comes and eNodeBs that goes, etc. So, if we look at the RNN case, what will the probability distribution on the final softmax, for instance, how will that change as your network is adding or removing nodes, etc. You would have to, in this case, you would have to retrain pretty much an entire model if you have the softmax as the probability distribution over all eNodeBs. So if you have an architecture like that, you will need to kind of start from scratch more or less every time. Of course, you can do kind of fine-tuning approaches to it, but conceptually, you kind of need to start from scratch every time. Another thing, very intuitively, if you add the top eNodeBs, which is like the most popular eNodeBs that a particular user happens to visit, you can get a pretty well working model. But in practice, if you have a system that is essentially dealing with all the traffic of Sweden at the same time, how do you actually calculate that per user? That's the tricky part. So, I mean, normally you would, I mean, we're seeing petabytes of data per day, essentially, for a single MME. So if you kind of stream it outside of the server, you essentially need a completely separate cluster just to deal with the data. So the cost kind of very quickly explodes in that sense. Yeah, and the argument for the final softmax layer is essentially the same for the embedding layer as well. How do you deal with those embeddings if you're kind of adding and removing eNodeBs and so? For instance, the previous eNodeB could be completely new eNodeBs and so. And like I mentioned, we're talking petabytes of data, so. Can we afford to actually stream data out from the MME to some other training entity? What's the cost of that compared to the cost of the actual MME? Like I said, you have about, let's say, 50 servers, COTS, off-the-shelf servers dealing with all of Sweden. 50 servers is not a lot in terms of, let's say you would have a Kafka cluster with Kafka streams being deployed here. So 50 servers is not a lot for petabytes of data where you actually need to do something practical with this, not to mention storage, etc. So very quickly, as you're kind of starting to add things here, the cost of actually maintaining a separate training entity kind of increases quite rapidly compared to like the actual function. So whatever you save by deploying this model, you need, I mean, if the cost is that we need to stream data outside of the node, the gains from having that machine learning model must be huge, essentially. Yeah. So flexible deployment, what we call this flexible deployment. So essentially we have the same product that is deployed in very small scale networks and exactly the same product that is then deployed in very large scale networks. So you have, let's say, an operator in China, which has hundreds of thousands of ENOBs. You have exactly the same software that needs to work in an enterprise system, a factory where you maybe have 1 or 2 or 3 ENOBs. The same system still needs to work exactly the same way. So ideally, whatever model you have that you train needs to be able to actually train and work in also in these very small scale situations. It doesn't have to work perfectly, but at least it needs to work. Yeah. Why we have the same software? They don't necessarily have to work in the same way. That's a very good point. Sure, that's true. But ideally, since we don't really, Ericsson as a vendor, we can't really control how customers will use our products. So, I mean, if we add multiple options, then we need to make sure that the customers actually enable the correct functions and does everything correctly. So there is a cost in terms of complexity, at least by maintaining like 2 different functions in that sense. But otherwise, that's a very good point. Right, so again, I mentioned tuning. So again, if we're a vendor, we're deploying a embedded model, which we have very little control over. So we just give it as a box to a customer, they hook it up. And what will then happen? Will the customer have a data scientist on site, understanding the model, how to train it, understanding the problem, etc., etc. Remember, customer is an operator is usually the people who actually work with deployments. That's a very small team compared to, let's say, the R&D resources of Ericsson. I mean, we have hundreds of thousands of people, but a customer that is actually deploying a new MME in this case, that's maybe 1 person. So that person has to understand both the MMEs and all the other network functions that's part of the network. So they have an extremely limited amount of time they can spend on actually deploying the MME itself. So we can't really rely on that the customer have an on-site team understanding what to do, how to do it, understand exactly what some hyperparameter means, and if it's incorrect, how will it actually, if they change some hyperparameter, what effect will that have on the model, and so on. So essentially what we need to do is make it extremely simple in the sense that, I mean, ideally it should just work with no specific configurations or anything like that. It should just work out of the box, ideally. So with respect to that, you can start thinking about for both the Markov chain that we discussed and the RNN. So what impact will our model choice here have on the actual customer experience when they actually deploy it? So if we're talking about hyperparameters, will those hyperparameters, I mean, we could, let's say, document and recommend different hyperparameters. But again, the same model ideally should work both in a small scale network and a large scale network. So every hyperparameter you adds complexity in terms of cognitive load on the user itself. And again, how much compute is needed, how much data is needed to actually train the model, all that stuff becomes very important since we don't have any control of the system itself. Again, you mentioned a recommender system in terms of confidence thresholds. So there we have it. It's a spoiler alert. Again, and yeah, and also model lifecycle management. And so I've mentioned that we cannot rely that there is some trained data scientist at the customer network. Can't really rely on that the customers have people in place that can kind of both monitor models as well as the MME itself and all the things that surrounds it. So how do we actually do that monitoring and I mean, if you have an automated model lifecycle management system in terms of kind of, I mean, there's a bunch of different tools nowadays where you can kind of define some evaluation metric that triggers retraining of the model and also triggers deployment and so on. But again, that's an external system, and you need to have some data. So even though it's an automated system, you likely will still need some form of expert that can monitor those metrics and the deployment if something goes horribly wrong, for instance. And again, in terms of lifecycle management, if we do have an offline training system, so again, as we're kind of selling the system to a customer, and they ask, well, how many servers do I actually need, and so on. And I mean, without knowing exactly the traffic model and everything, that becomes very hard to predict in terms of how much they need to buy and what to buy, how long will it take for the model to actually learn anything, etc. And similarly with as with recommendation systems, you also need to think about cold start problems and all that stuff. Yeah, and that's also this, I mean, it's a backwards way of looking at it, but how much data is needed to get a model to somewhat converge at least. Right, and also what I call debugging, yeah. Yeah. Yes, but what I meant with that is that it's two different systems. So the eNode B is one, let's say, machine, and that is kind of exposing its data. But the way the eNode B actually talks to the MME, that is standardized. So we cannot request data that is not part of the standards. It could even be that the eNode B is actually developed by somebody else that's not Ericsson. So we cannot rely that the eNode B will send some, let's say, auxiliary data that's not normally part of the standards. We can't rely on that. So that's what I meant with that it's isolated. It's not that it's like network-wise separated. It's just that they don't share all information, and there's no guarantee that we own all the equipment. Yeah. So again, usually what I like to, nowadays I think it's slightly more established in terms of interpretability and explainability, but again, this was a few years ago, so I tended to talk about debugging and explainability, but I think it's more established nowadays. But still, from a problem perspective, what happens if your model starts to diverge? I mean, you have some concept drift, for instance. Or if you, let's say you have some malicious adversary, what happens if some user starts to, some cell phone is hacked, and that cell phone all of a sudden starts to try and like very quickly transition between eNodes Bs, for instance. What will then happen with the model itself? And also fairness and bias. Is that something we need to think about in this particular case? Even though it's a network level model, I mean, naively you would think that it doesn't actually have an impact in that sense. But is that really true? What happens if a user is living in a rural area and so you don't have a lot of data for that rural area? Let's say there's only 1 or 2 or 3 eNode Bs in that particular area. So they're not generating a lot of data in terms of the transition probabilities to its neighbors, if we're talking about the Markov chain here. But if there's not a lot of data, that means that if you have some suboptimal implementation that happens to page other things that are not physically located to that InnoB, that could mean that your user gets a higher latency, for instance. So just because the fact that the user happens to be in some particular area or something, then you could have an impact on that particular user and their latency. So even though naively you would think that since it's a network-centric model, fairness and bias maybe doesn't have much of an impact, but the more you think about it, well, actually, it could be that just because you happen to be unlucky and live in the wrong place, etc. Yeah, and also again, if the model do misbehave, but I guess this is more known nowadays. So how do you actually communicate around this? I mean, traditionally it was called explainability in terms of models. So how to the end customer, how do you actually explain in an understandable way what actually happened and why the model failed? So imagine yourself, you're in the role of a machine learning developer and you have built this machinery and something breaks. Which model is easiest to reason about around explainability? How do you actually explain it to the customer? How do you make sure you don't get a billion different bug reports on something slightly misbehaving and so on? So if you think about that, which model would you prefer to have? A leading question, but at least for me personally, I would say it's much easier to explain a simple Markov chain, because this is the kind of most people, at least technically oriented people, can at least reason slightly around basic statistics, while trying to explain, let's say, an embedding layer to a non-machine learning person is very quickly you end up in magic land. Okay. So now that I've talked about all these different problems, and hopefully we only have a few people who fell asleep. So if we take all this into consideration in terms of the evaluation score, deployment, lifecycle management, etc. So which model would you pick? So if, let's say we do two models. So we have the Markov chain, we have the RNN. So let's do a hands up on Markov chain. Okay, so half-ish, and RNN. Okay, so we have a lot of abstainees, but we had 4 or 5 different RNN people. I'm curious, why would you pick the RNN?
I just think that maybe RNN is not the best solution, but at least it's closer to the current state of the art, like closer to neural networks, perhaps a different approach that's not an RNN, maybe like, how to say, like, something closely related anyway to deep learning would be better solution. And actually, I was thinking that if people like hidden Markov models, for example, then maybe you could try to work with a network based on graphs, for example. So that would be easier to
Sure.
explain to computer science people reason about it.
Yeah, yeah, sure. Sure. So I mean, you mentioned graph neural networks. I think you mentioned it at least. So I should mention that this work was done before graph neural networks were even invented. So, or rather, this was done pretty much at the same time as the first GCN paper kind of arrived. So that's why I haven't brought it up. But otherwise, that's like the first question I usually get. Well, have you tried a GNN? No, I haven't. But I think we will. I will get there later. But you do raise a good point. Is that when you look at it academically, most papers will tend to use some deep learning model in one way or another. And you could argue a lot around that, but.
I mean, I'm just guessing here, but you're overestimating the need of the accuracy of the model.
Yeah. So that led me into this slide. So essentially what this is showing, so here we're doing an accuracy at K plot, for instance. So accuracy is essentially exactly like you mentioned before. So here is essentially what would the accuracy be between these two models if we're only allowed to recommend one node B. And then K is kind of continuously increasing. So if we're allowed to page 5, how accurate is the model then, and so on. And essentially what we can see here, so we know intuitively, or rather empirically, we know that for this legacy smart paging approach, where we have this stepwise approach, we know that in step 2, in most cases, you need at least 90% accuracy for it to actually be better than the previous solution. And the reason for that is as soon as you go to like the next step where you page the whole tracking area, you get penalized so much for that. So as soon as you kind of transition later on in that algorithm, the number of signals kind of explodes. So you need at least 90% accuracy. And if we look at this accuracy at K slide, then we see that if you need at least 90% accuracy, the models actually behave pretty much the same. So the simplest model in this case, which is the Markov model, a Markov chain, and at this time the most complicated, most accurate model in terms of mean reciprocal rank we could find is what I call the RNN here. So we can see that if we need more than 90% accuracy, pretty much the model doesn't matter. That's the kind of the end result. Yeah, so intuitively here, I at least would pick the Markov chain just because of that simplicity. And then I think we will continue a bit more in terms of why it becomes interesting. Did that answer the question, Josef, or the comment you had before?
I don't know which one.
About you don't need as accurate a model. Yeah. And so here again is the comparison just a very simple slide showing the number of signals per second over a week in this particular case. Unfortunately, I've removed the scale here just because this is real data from a real network. So I'm not allowed to show that particular customer, but conceptually you can see basically cold start, we are already outperforming the legacy smart paging. And legacy smart paging here is when we page the historical list in step 2. And very quickly in this particular case for the Markov chain, it converges within 10-20-ish minutes, if I remember correctly, the kind of the x-axis here. So very quickly it reaches that.
I was just thinking, trying to understand the previous plot and the statement that the choice of model doesn't really matter.
Yep.
But is the paging cost scaling linearly with the amount of pages?
Depend on what you mean with cost. So if you mean CPU, in terms of CPU cost. Yeah. So, I mean, again, you could choose to look at it from a multi-objective optimization problem. So we want to reduce the number of signals as much as possible without sacrificing latency. So one definition, you could say that, maybe it's hard for you to see, but the right-hand column here is cost, but that's just a product between the latency and the number of signals. But maybe in the extension of your question is the cost linear in the sense that if let's say the top 80% of the paging is more expensive than the bottom 20 as an example. I guess that's the question. But I can answer is that the cost of a paging signal is the same regardless. I could mention that. So it doesn't really matter if we page a lot or very few. The individual cost of the signal is the same. did I answer? I'm not sure I did, but yeah. So this slide again, we can see again for the Markov chain, the convergence is really quick, and obviously the gains in terms of the legacy smart paging is orders of magnitude, I would say, better than the legacy one, where you use the historical value, historical list. But when I present this now, I realize that I probably missed a few steps in between. But we'll do that now. So why would I argue that the Markov chain is better than an RNN? Why would I do that rather than all the other stuff we've discussed? Is that when we discovered that the Markov chain was a feasible solution, as a developer, in the general sense, kind of your options really opens up. So then you can start thinking about, well, do I really need a big separate training cluster? Do I need all that data? I mean, it's so much easier to implement and reason around a Markov chain in terms of deployment than let's say an RNN. So when we discovered that and realized that we could just as well just use a simple Markov chain, we realized that we can actually turn it into an online model. I don't know if any people here were at, what was his name on the GAIA conference? River ML guy, Max something? Max Halford, yeah. So he talked a lot about online learning. And the Markov chain is an example of an actual online learning system in production in live networks, and has been in live networks for a couple of years now. At least in my experience, that's very, very rare. And just for that reason, and for like all the benefits I discussed around since we can put it inside the MME, that means we don't need all that infrastructure around it. We don't need that infrastructure for detecting the concept drift. We don't need all that other whole bunch of stuff theoretically, if we're able to make it work. So you can save a lot of stuff on that. Yeah.
How do you calculate the probabilities?
I mean, this is a super. Yeah. So the update will get to that, but the probabilities in the naive case in terms of the forward or inference step is quite simple. So in this case, if we look at the transition probabilities, so what you do essentially is just measure, you observe every signal that's being sent when you're going from one InnoB to some other. And what type of signal it is doesn't really matter. All you need to know is that some UE went from this InnoB to this other InnoB. And then you just count the number of transitions between those two. And then the probability distribution is just the count divided by the total count per InnoB. So essentially, yes, exactly. So we don't need a separate system. You've already kind of parsed all the messages that's inside the MME. So in terms of cache coherence and all that stuff, it's already in memory, it's already there. So essentially you get this calculation for free, essentially. You could even argue that this compared to the legacy model is, since this is a network-centric model, you only need to store transitions between InnoB pairs in some sense, while the legacy model saved, the legacy smart paging actually saved a list of 10 InnoBs for every user in the entire system. So in terms of memory consumption per UE is much lower in this case. So you're actually saving both memory and compute at the same time. Yeah.
Is there some kind of hand-wavy explanation for why the old algorithm fails at these peaks?
It's not that it fails. It's just a natural pattern in the data. So usually you get this peak is in the morning and this peak is in the afternoon. So this is usually when people go to work and the other one is when they go home. So it's not that it's particularly failing in this case, it's just that people are moving around more during the daytime.
So why is the market change not bad? Like what happens?
Yeah. So the short version is that the historical one was on the order of like a history list of 10. And the problem is that 10 is not nearly enough. You have transitioned through much more than 10 during the day. I mean, as you're going to work, you will probably transition through maybe possibly hundreds of eNodeBs just for one simple trajectory. So trying to figure out, trying to save where you were yesterday is just, yeah, it just fails. It's not a good model in that sense. But I mean, at the time when they did it, I mean, it was very hard for them to know because they didn't have any data. So all they could do was just guess, essentially. I think this is where I was, yeah. So let's get back then to the online learning problem or the online deployment problem. So going back, what happens when somebody adds an eNodeB in this case? Or even, let's say you add an eNodeB and the neighbors around that eNodeB, I mean, their transition probabilities will also change in some sense because you're kind of adding a new node and the handovers between the new eNodeBs, they will kind of change the legacy distribution as well, probability distribution. So what we did in terms of this Markov chain was just a very naive implementation where we added a decay factor to the transition probabilities. So essentially with some frequency, for example, let's say you have a transition count of, let's say, 100,000 for the last, let's say, 10 minutes. And then every 10 minutes, we just divide the transition counts over all its neighbors. And we just continuously do that. And if the transition probabilities never change, the probabilities will remain the same as well. While if you remove one eNodeB, for instance, in that case, then gradually the transition probabilities will shift towards the new probability distribution. And as the transition count, I mean, if you're continuously dividing by 2, for instance, eventually the value will reach 0, and then you can kind of remove that neighbor relation. Yeah. I think we even proved it in terms of, this was too long ago. So I think there was like a fixed pattern in the sense that you this frequency where you divide it versus the number of signals, that the changes or adaptability was fixed regardless of the frequency, essentially. So I think we did some proofs in terms of showing that the same model will and the same frequency would work regardless if it's a big system or a very small system, and so on. But I really don't remember the details. But of course, there is a lot of stuff you can do there. And you're correct in the sense that the frequency where you kind of reduce this number is, I mean, it's if we ignore the proof, in some sense, it's a balance between how fast do you want your model to converge versus how fast you want it to adapt to kind of changes. Online version of it, but yeah, absolutely. And so, like I mentioned here, there is this balance between the convergence of the initial model, the cold start problem, versus this adaptability to topology changes. Also, another mention here, honorable mention, is this confidence threshold that we added. Rather, I mean, you could easily think that if you have a Markov chain and you have some probability distribution of its neighbors, the naive solution is just say page the top 10 of its highest probable neighbors. So you would always page a fixed length of 10. But if you actually start looking at confidence thresholds, so you say that page however many eNodeBs of that neighbor, of those neighbors, page however many you want, as long as you reach at least, let's say, 90% confidence threshold. So that actually had a pretty significant impact when we started looking at the confidence rather than a fixed length. And the fixed length is also a bad choice in terms of this, again, this flexible deployment. So if you have a very small network where a single ENOB, perhaps it only has a single neighbor, so having a fixed list in those cases doesn't really is not really optimal. While if you have this confidence-based approach, it's much more robust in terms of different types of networks and so on. And what we've found is essentially that these confidence thresholds, we could put pretty stable default values for those confidence thresholds, and it would work relatively well independently of where in the world and which operator you happen to be. And it tended to end up at something like 99% confidence, I think. Do you remember, okay? Something like that. So much higher threshold than you would initially think. Or at least what I would initially think. Yep. So let's go into the complicated stuff in 15 minutes or less. So if we want to implement this in a super fast and very complicated way, this is one way of doing it. Yep.
Fine question. So what's the recall for the top 100 transition states on average? Do you remember that?
No, I don't remember.
What do you do? Is it like 50% or 95%?
I don't remember. This was too many years ago. Yeah. Anything else before we go into the... So I should mention that this is not for the faint of heart, but if you really like weight-free concurrent algorithms, stick around. I suspect nobody really wants to listen to that, but so if you have any questions regarding the machine learning stuff, it's open. It's an open floor now. And if you're lucky, if you ask too many questions, I won't get to the atomics.
Can you consider time how long the user is idle in the model?
If we try to model how long the user would be idle, is that your question?
No, not how to modulate. I mean, like, you can affect how to A and B based on that. If the user going idle for 1 hour, then it should be totally different, not a neighbor.
Not for this use case, because at this use case, we, when we're paging some user, it needs to be paged now. So for this particular use case, it's not really interesting if it's been idle for, let's say, X, Y, or Z hours before. But that is a valid use case in other cases where, let's say, we want to maximize the time the user stays idle. So, I mean, we could fiddle around a bit with like the state of the user so that it stays idle for a longer period and so on.
But the transition matrix should depend on the time the user has been idle. Because the probability of moving to points further away.
Essentially, I think we would model that in the RNN, I think. Let me see if I remember. So I don't remember. I mean, we tried obviously to model the previous ENOB here is like the trajectory of where the user has been. So, or rather where it's coming from before it went idle. If I remember correctly, we did variations of this where we also include like the relative timestamp of those transitions. So you would know that the last transition for the previous ENOB was 10 hours ago or whatever. 10 hours is a bad value, but implicitly you would model that there. In these two examples, we didn't really do that I brought up here. But the assumption stays the same, that the model doesn't really matter in that sense. of course, you can reason about why that is. I mean, you could have a lot of theories in terms of why we always need to page, let's say, 10 InnoDs for every attempt. Of course, you could reason about that. My current hypothesis is that we don't really know where. I mean, if you have, let's see if I can go back to this one. So my hypothesis is that if you're in this position, let's say, in reality, you don't really know if let's say your last InnoB was this one over here, and you're in this position. You don't really know if you are at this InnoB or that one or that one. All of them could be equally likely if you're like in the middle, and they have equal load. So you need to always page a group of them to kind of pick up on that, let's say, variance in the transition. Bad word. I'll take that back. But yeah.
But you would increase the number of pagings that you need to do depending on the time, right?
Yeah.
If it was 5 minutes ago, I could page 10, and if it was 10 minutes ago, I could page 20.
That's a good point. I don't think we modeled that specifically for the Markov chain, but that's a good point. But like I said, I'm pretty sure we modeled it for the RNN variations and all the other different billions models we did. I mean, obviously, we also did order and Markov chains and so on to see if the actual trajectory mattered. So, I mean, if let's say you do an order 2 Markov chain and you're in this position, if you know that the previous InnoB was this one and the previous that one, you can maybe guess that the trajectory is going in that direction. Didn't matter. Yeah. More questions? Yeah, so in this particular case, this actually includes the training time of this online model. So the first step here is the convergence time, essentially. So it's right, but I don't think we actually looked at that in particular. But one thing to keep in mind is that as you're changing the adapting to that topology change, that is only a local update for that InnoB and its neighbors. So it's not a full network topology update in that sense. So even if your model is misbehaving locally around a particular InnoB, it still means that the rest of the whole graph is approximately correct. So the impact of like a single InnoB that gets added or removed is relatively low. I mean, we didn't really look at hybrid models like that. So the Markov chain in this particular case is all. I mean, it's all network level. So we don't really model user behavior at all in that particular case. I'm not sure that answered your question or not, but okay. There were some more hands.
I was just wondering back when you did this work, like how much effort went into the neural network model before you talked about trying this?
In terms of modeling, I would say I don't know, 60, 70, 80% went into more sophisticated models. But
When did you decide to raise the point?
go for the simple one, you mean?
Yeah.
the way in our group we tend to work is that when we get to the modeling side of things, it tends to be very, very open-ended. So we want to try the simplest thing and the most complicated thing, just to get like, okay, so where are like the the edges of our, like, how reasonable is this solution? What's the best performing one versus the worst performing one? And then it's, I mean, when you've done that kind of mapping of where you are in terms of accuracy, lack of a better word, then after that step, then you're in like the design phase. Okay, so given this is the range of options we have, what can we actually do with it? So I would say at this particular point, I mean, when we're in the modeling phase, I would say we're not really thinking about it in that sense. So it's much more open-ended. Just try and throw whatever stuff you can at it.
I have seen a lot of projects with this big ones, big, complicated, expensive things.
Yeah.
When you just think about the business case and pick the correct metric,
Yeah.
of the comparison.
Yeah. I would say one thing that is very, very different just because it's online versus offline is that, I mean, normally you do your modeling and all that stuff around it. And then you're conceptually done. I mean, very simplistically said. But I would say in this case, since it was online, after the fact that we figured out that we could do this online, we spent a very large proportion of time just making sure that the model would behave very, very well in an online setting. Since we can't really retrain the model, we can't restart it, we're very limited in terms of what we can do. So. I mean, in terms of the total time budget for the project, I would say the majority of it was more like testing robustness. How robust is the model? How well does it work? Does it misbehave in certain cases, and so on. Yeah.
And I'm just thinking about this accuracy metric here, because you actually, if I go from 90 to 95% accuracy improvement on that first paging, you actually would reduce the number of times you need to page the whole network by half.
Yep.
So it seems to me that because you have this exponential effect in the number of pages to the whole network, even a marginal improvement of the accuracy would have big effects.
Yeah. I mean, essentially that's what we're seeing here. Yeah.
Because that could make a good argument for why a more advanced model would actually make sense.
Yeah. Yes, but actually, I mean, I should add. Maybe it's not part of this slide, but of course, when we did this, we're not, in this particular case, we actually did write a whole simulator for the full behavior in some sense. So how would this model actually behave with a full paging algorithm, including like the tracking area pagings and all that stuff? And what we see here in terms of the cost or the number of messages per messages per paging and so on, that is including all 4 steps. So it's like the total performance of the entire system is what we care about, and not only the accuracy of the model. And so when we compare it with that, then it turns out, unfortunately, I think the RNN as an example is not part of this table. But then it turns out that I think the cost here was roughly the same as the Markov one. If I remember correctly, maybe I'm lying now, but I think it was roughly the same.
Pick on the statement that it doesn't, the model choice.
Yeah. I think it boils down to that a model can only reach, again, that's the hypothesis. Any model can only reach a certain level before that noise that we can't really account for, which is like the local E node B selection, where we can't really model that local E node B selection. And we can't model that not because of the model, but because we're lacking the data and the information to actually model it. So all models will kind of tend to eventually reach the same level. That's the hypothesis, at least.
By increasing the number of pages.
Yeah.
So with online learning,
Yeah. Yeah. I mean, we did test variations of that, and that's again relates to this, where we really spent the majority of the time of testing the robustness in these like extreme cases. So that's the short answer. So we did test for it, and also we really spent a lot of effort making sure that individual, I mean, since the model is very different from the legacy one, and all of a sudden you could have a difference in terms of behavior, in terms of which InnoDs that the model will choose to page. So, I mean, if we would have made a mistake here, for instance, let's say you have one InnoD that just by chance happens to be a neighbor to many other InnoDs. So that single InnoD will by chance kind of be paged a lot, even though it's a relatively low probability that InnoD is there. So we also did a lot of tests around making sure that the individual InnoD load stayed the same or lower than the previous model, and so on. And it all relates to that. But going back to the original question in terms of these, it has a specific name in telecommunication, but these kind of abnormal events for like New Year's Eve or concerts and stuff like that. And the thing is that you're right that a model which is updating its topology too frequently will eventually kind of be suboptimal in that local area. But at the same time, as people move away from that area, it will eventually converge back to like the true probability distribution. Hopefully that answered your question. We're out of time, so we can do a few more questions if you want, but I don't have time to go through this, unfortunately. But you can ask me about it later if you want. Okay, thank you.